Schönen guten Abend, herzlich willkommen bei Nachts auf der Sternwarte. Good evening, welcome to Nachts auf der Sternwarte. We'll have a fantastic talk first, and then afterwards a tour of the observatory, if you wish. But first of all, Prashin here is going to take us on a joyride through the galaxy. Prashin has been a postdoc here for 5 years now, and 6, and I'm looking forward to the talk.
Thank you, Oliver. Hi, everyone. Thanks for coming. I am going to tell you a bit today about fast stars, the fastest stars in the galaxy. But to give us a bit of context, let's start with some more down-to-earth speeds. Okay, so one of the fastest things that we'll probably be on in our lives is an aeroplane. You know, a typical velocity is around 800 kilometers per hour. I'm from London, so a lot of my examples will be related to London today. And, you know, with that kind of velocity, you'll get between Vienna and London in about 2 hours, give or take Ryanair delays. But let's take a step up, not look at an aeroplane, but a satellite. And a typical speed for a satellite orbiting around the Earth is around 3 kilometers per second. So to put that in context, the aeroplane is around 0.2 kilometers per second. So much, much faster now. And this gives us a chance to think about orbits for a second. What does it mean for this satellite to orbit around the Earth? Well, it means, as opposed to the aeroplane, which needs an engine and power to keep it going, this satellite, if it has that velocity, can circle around the Earth with no energy input required. It basically falls around the Earth, pulled in by the Earth's gravity, forming a circle and going all the way around. But if you increase this velocity just a little, say from 3 to 5 kilometers per second, this satellite now has enough velocity to escape from the Earth's gravity. This is called the escape velocity. It's reached the escape velocity required to get away from the Earth. So we're going to take a step out now and not think about things going around the Earth, but rather the sun going around the galaxy. So yes, our Earth goes around the sun, and the sun is one of about 100 billion stars in the Milky Way. But it also is on an orbit, this time an orbit around the center of the Milky Way. And the velocity it has to be able to have this circular orbit around the galaxy is around 230 kilometers per second, so significantly higher now. But again, just a slight fraction more, if you take this velocity up to about 550 kilometers per second, the sun would have enough velocity to escape from the galaxy. And these are the stars we're going to talk about today, stars which have high enough speeds to escape from the galaxy. We call this, you know, this like threshold speed you need to be able to get away, the escape velocity. And here we see a curve of the escape velocity you need to get away from the galaxy as a function of the distance away from the center of the galaxy. So here's the sun at around 8 kiloparsecs. Its actual velocity here, 230, and the velocity it would require to escape up here, 550. And you can ask what this velocity is at different distances from the galaxy center, and it's this green curve, the escape velocity curve. So this curve divides this speed-distance plane into two. Anything above the green line we call a hypervelocity star. They have enough velocity to escape. Things below the green line are bound to the galaxy, and they will orbit around for, you know, billions and billions of years to come. But as soon as something gives you a little push, a little nudge to get you over that green line, then suddenly you have enough velocity to be able to escape. And yeah, this is a concept of a hypervelocity star. So why are these interesting? Well, it's precisely because as soon as you're above this green line, you're pretty much gone in a blink of an eye, compared to the timescales we normally think about with galaxies, billions of years. As soon as something gives you that little nudge, then you'll be flying away. It's as if you look outside the window and you see a rocket. You know that rocket was launched recently. So we would need to know what is launching these hypervelocity stars, if there are any at all. So these are the two key questions I want to talk about today. Do these hypervelocity stars exist? And if so, what accelerates them to such high speeds? So a bit more of an outline of what we'll talk about. Firstly, a step back and ask, how do we even measure these velocities? Then discuss how many hypervelocity stars we know of, if any. Talk about the origins, what physical mechanisms in the galaxy get us to these speeds. And then finally, a word on the fate. What will happen to these eventually? But first up, how do we measure these velocities? So for everything, there are three possible directions where it can move in: forward, backwards, up, down, left, right. So to measure the velocity of a star, we need to measure all three components of its velocity in these three directions. And we do it in two slightly different ways. So to get the velocity of the star as it travels across the sky, that velocity we call the proper motion. And the way you measure it is quite intuitive. You take an image of the sky, go back sometime later, and note how the position of the star changes. So you do this going back to the same position on the sky and taking these measurements, and you can infer its velocity in kind of two of the three directions. To get the velocity towards or away from us, we need to do something slightly different. In this case, we take the light from the star and split it up into its constituent colors. I call what's called a spectrum. There are particular signatures, particular wavelengths in the spectrum where we don't see much light. These are these absorption lines, and they tell us what chemical composition the star has, what it's made of. So in this case, this star is made of some hydrogen, sodium, some calcium. If the star has some velocity towards or away from us, however, this spectrum we observe is shifted. If it's moving away, it gets shifted to the more red wavelengths. If it's moving towards us, it gets shifted towards the more blue wavelengths. So when we measure a spectrum, we can compare what we observe to what this kind of position the absorption lines would have if the star was at rest. And then we can infer, we can learn about what velocity it has towards or away from us. And that's called the radial velocity. So they're the three components of the velocity we can measure and how we can do it. But thankfully, we don't need to go star by star because we've built telescopes which can do this automatically. So this is a picture of ESA's Gaia Space Telescope. And it has equipment on board to do exactly this, measure the velocities of stars, but now 1 billion stars. So this video will show kind of how this Gaia telescope scans across the sky, measuring velocities of 1 billion stars. And while it's doing that, I'd like to tell you something about the precision that this instrument has. Gaia can measure, if I were here, if I am here, if someone else were in London and held up a single human hair, Gaia would be able to measure the width of that hair from this position here in Vienna. So about 1,000 kilometers away, Gaia has the accuracy to be able to measure the width of a single human hair and do that for 1 billion stars. So a really, really impressive feat of engineering. So Gaia has collected tons of data, and it's got incredible results spanning all kinds of questions in astrophysics. But what does it have on hypervelocity stars? So this paper from 2019 by Marchetti et al. Answered this question. And it went to this enormous database of Gaia stars and put them on this plane, speed versus distance. And the results look like this. So below the escape velocity curve, is where the vast majority of stars are, most of them here, with a similar velocity to the sun, something around 200 and something. But there are a few things scattering above. So a good sign that we have hypervelocity stars here. So to make this a bit more quantitative, we can look at the distribution of velocities that are measured, that are shown in this diagram. That's shown here. We have velocity on the x-axis, or the speed on the x-axis, and the number of stars with a given speed on the y-axis. So, and we have three different distributions here. So at first, in black is the full sample. 7 million of the stars from Gaia with the required measurements to take this 3D velocity. And you can see it has this enormous tail, but reaching out to huge velocities. So there's 1,000, but it goes up to 10,000. However, these measurements come with some errors, some uncertainties. And when you filter out the stars with very large uncertainties, we're left with the red distribution. And you see this tail of high velocities gets shrunk all the way to here. That's saying that we really need to account for the uncertainties in our measurements when looking for hypervelocity stars. When you then ask, when accounting for these uncertainties, which stars are likely to lie above the green line, you're left with this cyan distribution. And that's just 125 stars out of this initial sample of 7 million. So we're talking, for candidates of hypervelocity stars, it's a real tiny fraction of all the stars out there, but they're there. So now we can start to ask questions about them, like where are they and where are they coming from and where are they going? So this is a diagram showing the positions and the velocities of these hypervelocity stars. The ones in red are traveling away from the Milky Way. The ones in orange are coming towards us. We'll come back and talk about that more a little later. But just to give you a 3D perspective on where these stars are and where they're going. So they're there, and we can find them. What is causing them to have such high velocities? So there are a number of different theories or explanations, but interestingly for today, they all start with binary stars. So a binary star system is two stars gravitationally bound together. And I thought to myself, wow, what could be more appropriate for Valentine's Day? Is anyone here on a Valentine's date, perhaps? No? Well, that's probably a good thing. Because to take a binary star and get a hypervelocity star out of it, one of two things has to happen. Either one of you explodes, sending the other one hurtling away at 1,000 kilometers per second, or, and maybe even worse, a trio splits you up. So you see this guy in the middle here, pulling in one of the stars and flinging the other one away, again at 1,000 kilometers per second. Not very romantic. I'm glad there's no dates here tonight. So these are the two main kind of channels that you can form hypervelocity stars. And to give them kind of more scientific names, we have type 1a supernovae, when one of them explodes, and a three-body encounter, when a third body, the gravity of a third body causes one star to escape. So we're going to go into both of these in slightly more detail now, starting off with type 1a supernovae. So what is a type 1a supernovae? As I said, it's to do with a binary star system. And in this case, the binary is formed of one regular star, say something like the sun, but the other star is a white dwarf. And a white dwarf is what we call a stellar remnant. It's the product of the end of a star's life. The sun, when it runs out of fuel, will turn into a white dwarf. So you have this binary of a white dwarf and a regular star. And when they get close enough, the white dwarf can start pulling matter away from the regular star. once it's pulled away enough mass, once it passes some threshold mass, then the white dwarf can explode. And this is the classical picture of what a type 1a supernova is. It's what I was taught in my studies some 10 years ago. The picture has changed, however. There's another way of forming type 1a supernovae, or another possible scenario that can produce them. So that's not a white dwarf and a regular star, but rather two white dwarfs. So the basic process is the same. The two white dwarfs get close together, and one accretes mass from the other till eventually it explodes. But there's some important differences between these two scenarios that make it a very interesting and an interesting question, which is getting a lot of research. So white dwarfs are called degenerate stars, and the case where we just have one, we call a single degenerate scenario. When there are two, we have a double degenerate scenario. And this difference ends up being quite important, because let's ask what happens to the other star, the donor star, the one that is losing mass. What happens to that after the supernova? Well, assuming that it survives, then it gets a little kick in velocity. See that in this little animation again. This is material from the explosion hitting the other star and giving it some momentum to move away. But it also gains velocity because the velocity it had in its binary orbit, once the explosion occurs, that velocity is now freed up and the star can zoom off in a direction out of the galaxy. The two different scenarios of type 1a supernovae make very different predictions on what this orbit velocity should be. In a single degenerate scenario, the stars can start transferring mass to each other when they're quite far apart. Whereas in the double degenerate scenario, because white dwarfs are so much denser, they need to be much closer together to start transferring mass, and therefore they have a much higher orbit velocity. And you see that in this diagram here, which shows orbit velocities of double degenerate white dwarfs can reach 1,000 up to 2,500 kilometers per second, much lower in the single degenerate scenario. And this other source of velocity, this kick you get from the explosion, is actually quite small. So it's kind of counterintuitive that you have this enormous explosion, but the reason the star ends up flying away is not the force of that explosion, but much more importantly, the released orbital velocity. But this prediction for double degenerate type 1 supernovae then is that there should be white dwarfs traveling through the Milky Way with velocities of a few thousand kilometers per second. And that's exactly what was discovered in Gaia. First in this paper in 2018, and again in 2023, finding slightly different samples. We now have 7 examples of white dwarfs with these enormous velocities. The double degenerate 1a scenario, this is the first clear evidence we have that it happens, and is opening the door to try to study this process in much more detail. So that's supernovae. If we move on to the other channel that you can produce these hypervelocity stars, that's 3-body encounters. And in this case, it's a black hole splitting apart the binary stars. So watch this again. The red star gets pulled in, and the blue star gets flung away. It's an example of what can happen when you have 3 gravitating objects. And if 3-body encounters lead to chaotic orbits such as this. So I'm not the only one who's kind of made the link between these kinds of physical phenomenon and something Valentine's Day related. A paper about this kind of thing went by the name cosmic ménage à trois. Another context you might know this phenomenon from is from the solar system. When we send out satellites to the outer solar system, it uses a phenomenon called a gravitational slingshot, gravity assist. So if you watch the pink dot here, that's a Voyager 1 satellite. And as it crosses Jupiter, its velocity gets a big kick, allowing it to travel out to the outer solar system in a reasonable timescale. It's exactly the same physics that we're talking about here, but now with stars and black holes. And in particular, the black hole at the center of the Milky Way. So this particular combination, where you have a binary star system and a black hole, and a three-body encounter between those, is called the Hills mechanism, and it was described by Hills in 1988. So the black hole, we now have exquisite data of it, such as this image of the black hole in the center of the Milky Way from 2022. Some 30 years later, after this prediction from Hills, we finally have a concrete example of a star ejected from the Milky Way's central black hole with a velocity of 1,700 kilometers per second. It was discovered in 2019. And yeah, I'll just show you one example of how we know that this star came from somewhere near the black hole. So what I'm about to show you is a diagram showing where these hypervelocity stars came from in the plane of the Milky Way's disk. So the Milky Way is kind of pancake shaped. And we're going to ask, where do these hypervelocity stars come from when they cross the pancake, cross the disk? And that's shown by these colored ellipses. They show for each hypervelocity star candidate where they could have come from. The galactic center is here in red. As you can see, there's a couple that get near it, but really these areas that the hypervelocity stars could have come from are very large. These are all the other candidates. The discovery from this paper looks something like this. So you really have to zoom in to the center of the image to see the possible positions where this star could have originated. And it, perfectly coincides with this galactic center. The chances of something like this happening by coincidence are around 1 in 400. That's a calculation done in this paper, which is about as certain as you can get when you're playing these games of where do things come from in the galaxy. So this is kind of concrete evidence that the Hills mechanism is taking place and ejecting a star here at 1,700 kilometers per second. So just to summarize everything I've told you so far, hypervelocity stars are defined as stars with enough velocity to escape the Milky Way. And we have around 100 candidates in the Gaia data. I've given you two possible scenarios of where they may have originated from. A three-body encounter with the Milky Way's black hole. And we have a first concrete example of this discovered some 5 years ago. And the second channel is its type 1a supernovae. The discoveries of white dwarfs with these enormous velocities are a kind of smoking gun piece of evidence that a particular type of 1a supernova, the double degenerate scenario, is occurring and allowing us to study double degenerate scenario in much greater detail. So that's everything I want to tell you kind of about the scientific context of what we can learn from hypervelocity stars. I just want to leave with a few words on what's going to happen with them in the future. As I said, this diagram shows the hypervelocity stars traveling away from us in red. Those stars will, by definition, escape from the galaxy and enter intergalactic space for what will be quite a lonely existence. They imagine a night sky without any stars in. Eventually, these stars will be in such empty voids of space that that's all that they will have in their skies. But a handful of them will end up crossing other galaxies. The Milky Way isn't isolated in the universe. There are galaxies scattered all around them, all around us. And eventually a handful of these hypervelocity stars leaving us today will cross other galaxies. So these yellow hypervelocity stars, the ones arriving at us today, it's possible that some of them may have come from other galaxies. Making that connection concrete will require a lot more work and a lot better data. But the predictions are that there should be some of these stars, intergalactic travelers coming from different galaxies that will be crossing us today. So despite most of these having a very lonely fate, a handful of them, a sprinkle of them, will end up being one of the few intergalactic travelers in the universe. And that's all I'd like to tell you about hypervelocity stars. Happy to take any questions.
Thanks very much. Other questions?
You mentioned that the velocity for a satellite is 3 kilometers per second, but I know that it's 8 kilometers, and the escape velocity from Earth is 11.2, not 5.
I'm glad you asked that question. The numbers I gave earlier for the orbital speed around the Earth and the escape velocity are once you get the satellite into orbit. The numbers are different if you want to get something, if you want to escape from the Earth's surface. So there, if you want to get from the Earth's surface out into space, then it's indeed 11 kilometers per second. But yeah.
But when you want to put a satellite into orbit into Earth, the satellite have to be 8 kilometers per second fast, not 3.
So that particular number, again, this number 3 was representative of one particular orbit. Roughly, it's a geosynchronous orbit. So a satellite which goes around the Earth at roughly and stays above the same position. There will be different velocities when you go to different orbits at higher positions.
Going farther from the Earth, the velocity shrinks.
So if you have a higher orbital velocity, it means that you're closer in. And that's because when you're closer in, the force from the Earth is greater. So you need a larger velocity to keep you in an orbit around it. And if you travel further out, the orbit velocity becomes lower.
Yes. But I have a second question. Is this three-body encounter also possible with another star instead of black holes?
Yes, indeed. And well, the thing about three-body encounters with stars is that for most of the galaxies, stars are very far apart. So the chance that you'll have an encounter is very, very small. There are some called star clusters, which are very densely packed with stars. And there we do expect that encounters between 2 or 3 stars, or even black holes, neutron stars, will cause some of them to be kicked out. That does happen in some places.
Hello, I'm a space beginner, and I just had a question, and probably obvious, but is a hypervelocity star a shooting star?
Ooh, good question. So, unfortunately, I think all of these hypervelocity stars that we found in this Gaia data, they're going to be way too faint to actually see. So, yeah, the shooting stars are going to be something else. They're much closer to us.
Is there a chance for these intergalactic stars when they pass through the Milky Way to be caught in the Milky Way and stay here?
So there's a chance, but probably a very small one, because once you have a very high velocity, it's hard to slow you down. Yeah, it would need to be a very, very rare orbit that brings the hypervelocity star near to something massive in a very particular way and interact possibly with a third star to make that possible. Typically, yeah, these things will shoot through at the velocities that they have.
Is there any pattern to the spectral types of hypervelocity stars, or are they just a more or less random sample of the entire stellar population?
So, of most of the hypervelocity star candidates from Gaia are fairly young, OB stars. The one that was, the one that we can link to the galactic center is a main sequence star. And actually, that one wasn't discovered in Gaia. That was discovered in a much smaller survey, not looking for hypervelocity stars at all. It was kind of a serendipitous discovery. But yet the selection for this other survey may guide a possible way to find more of these that are coming from the galactic center.
I was wondering, so since you said that the Gaia ones are young stars, because I was wondering there's also type 2 supernova for the young stars, and these massive stars, they're often in the multiple systems with multiple stars. So is there also papers on these young stars that get to escape velocity?
So most of the work I know about young stars getting to these high velocities are more related to the three-body ejection. Young stars kind of getting ejected via type 2 supernovae. I'm guessing that the kick velocities that we saw from these type 1As, if we see a similar thing for type 2s, which I'm very uncertain about, then maybe that's not enough to kick you out of the galaxy. But yeah, potentially if a young star, a binary, went type 2 supernova, then we could see something similar, but I don't know.
But a white dwarf is an old star, not a young star.
Yes.
But why are you speaking about young stars when these white dwarfs that were discovered are old stars? These 7 white dwarfs.
So the young stars I'm talking are mainly the candidates for ones which have come from the galactic center, come from near the black hole, not the white dwarfs in the type 1A scenario.
Do you know if the authors by chance check that if the hypervelocity star is coming towards us, if they are coming from the direction of Andromeda or like some of the other galaxies?
So there's hints that some of them might be coming from the LMC. That's a large Magellanic cloud, a dwarf galaxy, which itself is orbiting around the Milky Way. And that could be interesting because even then there would need to be some process which has ejected it from the LMC, possibly the LMC's own supermassive black hole. And this would be some of the first evidence of the LMC's supermassive black hole. For galaxies further away, I don't think there's any yet. I don't think the data is good enough to make any connection yet.
That's cool, thanks.
Hi, Prashin. So is there now any, I mean, you say they shoot out, yes? So to trace them back to the center is in principle a straight line back, unless, of course, space-time gets curved by whatever dark matter, etc. So with these binary stars, etc., can they now use these high velocity stars to also, by tracing them back, to see if there's curvature due to dark matter or visible matter?
So yeah, that's kind of one of the most exciting things you could do with these. Because once you know that the hypervelocity star has come from the galactic center, that's a super precise location where we know it's come from. The problem with this one star where you can make the connection is that it's too fast. Like the gravitational potential between the galactic center and us, you change it in what reasonable amounts and it doesn't affect the trajectory hardly at all. So yeah, you'll need to find a few more of these to be able to do that. What you can constrain is the solar peculiar velocity. So you get competitive constraints on the sun's peculiar velocity from the local standard of rest, just from the one.
Thanks. Okay, then thanks, Bosch, again.
Thank you.